Hi everyone, my name is Marcelo Forets and I will present efficient reachability analysis of parametric linear hybrid systems with time-triggered transitions in collaboration with Freire and Christian Schilling. The scope of our work is hybrid automata, a formalism that describes systems which makes continuous dynamics with discrete transitions. As a very simple example, let me consider the model on the picture, which has one location and one self-loop. The flow is specified as an exponential decay law, but more generally you can take any linear time invariant system with non-deterministic but bounded inputs. The condition to stay in a location is called the invariant. In this model it is that the time variable cannot exceed some given sampling time plus zeta, but in general it can be a polyhedral set. The condition to take a discrete jump is called the guard, and when a transition takes place, state variables are updated instantaneously according to the reset map, which is assumed to be an affine map in our case. So our running assumption is that guards and invariants are time triggered, in the sense that events only depend on the clock variable. The semantics of this hybrid automaton corresponds to a common setting in which a digital controller follows a wall clock and sends a periodic signal at multiples of a given sampling time. The transitions may lie in some uncertain interval around a nominal value, which gives rise to non-deterministic switches, when a zeta here is not zero, but it can be an interval. However, if the signal deviates from an exact multiple of the sampling time, the following signals will not drift because the reference is still given by the wall clock. So, numerical simulation of hybrid automata using standard differential equation solvers has no shortcomings. For instance, violations of invariants or entering the guards may go undetected. And to detect when trajectories enter the guard or when trajectories leave the invariant, all these solvers implement zero crossing detection using root finding. However, this may introduce spurious behaviors because numerically approximated states may lie slightly outside the guard of the invariant, so constraints have to be relaxed. In addition, if you consider non-determinism in the model, then the number of required runs to manage the coverage problem increases exponentially. The second motivation to our work is that simulation timescales of fast-switching controller dynamics usually take the order of nanoseconds range in the simulation, meaning that we require thousands of discrete transitions. So, although set-based verification is a viable approach to this problem and it does not suffer from missed jumps, we have to devise methods to efficiently mitigate the over-approximation error with respect to the exact flow pipe in the presence of complex dynamics. So, let me describe a high-level view of our workflow. Given a model of the system and one of more requirements, we first reason about the nature of relevant discrete events and then solve a set-based recurrence written on the top right, using a specialized algorithm for the case when the system has parameters that are fixed or when the parameters are uncertain. We then apply a discrete map that takes into account the guards, the reset maps, the invariants, and iterate the continuous and the discrete post operators until the given time horizon or a fixed point is found. We end up with a flow pipe that is guaranteed to over-approximate the set of all possible trajectories of this computation, as you can see pictured in blue, and this result can be used as an algorithmic proof that a system is safe. These implementations that I have introduced here are available in our open source library, Julia Rich. Now let me give some comments about the continuous post operator. Conservative discretization schemes will let us compute a set enclosing all possible trajectories for all points in a given initial set within some interval of time. Then, once we have discretized, we have to solve a set-based recurrence using one among several methods that are available, and the intuition behind this recurrence is that it propagates the solutions of the flow in dense time. To represent sets of points in the Euclidean space, we have used sonotopes. These are centrally symmetric convex polytopes characterized by a finite set of generators, and Minkowski sums and linear maps can be computed efficiently. Moreover, it is known that by a suitable reordering of this computation, approximation error can be avoided completely and this results in a very precise flow pipe. This means that we have a wrapping free. However, if A is uncertain, we have considered another method from the literature in which we have to compute approximations using interval matrices. Now, this suffers from problems because computing tight approximations of interval matrix products is hard, and it does suffer from dependency problems and wrapping effects. On the other hand, there are some good news because the dimension of the system doesn't increase with the number of uncertain parameters in contrast to other approaches. Since the clock variable in our assumption evolves independently from the other state variables, we can reason about the transitions in isolation. So you can see here on the left the case where switches occur at exact multiple of the sampling time, so zeta is equal to 0, while on the right switches may occur at any time when the guard is enabled. So you will have intervals around the sampling time. So in practical situations, the case with jitter is often more interesting because we can model inaccuracies in controllers, but this case is also harder to analyze. To work with time-triggered systems efficiently, the main idea is the following. So, because the transitions are time-triggered, we can reason about them before actually computing the flow pipe. For example, we can compute the upper bound on the right on the invariant, and the lower and upper bound when the guard is enabled, that would be T1 and T2 in the middle. So this will give us integers K1, K2, and K3 in this sketch, and it tells us how many sets we have to compute in advance for our recurrence of flow pipe, and in this way we can avoid expensive geometric intersection operations. In general, we may also have to use a clustering strategy when there are several reach sets between T1 and T2. Now, the benchmark that we have considered consists of an electrical engine that pushes the inner side of a brake caliper against a brake disc that is connected to a car wheel. The model is non-deterministic, and two sources of uncertainty are given: parameters and jitter on a discrete controller. For reference, the original evaluation used a tool for nonlinear systems called FlowStar, and it took around 13 hours to compute. Let me give some details on the model. So the original Simulink model is nonlinear, and here we use a linearized model with a discrete controller proportional integral, like represented here. Four state variables of the model: the motor current, the brake position and acceleration variables, and the clock variable, which evolves independently of the rest. The purpose of the discrete controller is to sample the distance between the disc position and the brake position. And with respect to the parameters of the controller, you can see these are K and the K's here, and they are physical parameters of the hardware. So we are interested in verifying that once a caliper's position X reaches a certain threshold, X0, the brake disc gets in contact with the wheel and deceleration happens within some time bounds. So you can see here that the requirement for maximum elapsed time, the idea is that to get epsilon as small as possible, and with respect to the velocity, we would like that the velocity stays below the given value, Vr, upon contact. Let me show you in the following plots example results with position of the disk at 0.05. So you can see that the flow pipe is entering the desired region, starting from the contact time shown in the green dashed line over there. And similarly for the velocity of the disk, of the caliper, you can see that the maximum velocity does not exceed the value Vr here. We have computed these operations given a flow pipe using calculus with support functions, which is very efficient. We have conducted an extensive set of benchmarks. So the summary is that we consider three settings, either with fixed parameters, with just fixing just one parameters of the system, but impacting several parameters as well in the option 3. So we also consider scenarios with and without jitter for comparison, and different step sizes as well. What you have seen in the first table that I am showing is that the width of the current and of the position of the final reset are used to measure the accuracy of the result. You can see accuracy gets better by reducing the step size, and we can get a very good accuracy results within less than 10 seconds. This column of time is a computation time. These computation times in all the tables that I'm showing are conducted using a normal laptop. The case with jitter is also harder, but we can verify the property using a smaller step size as well, as you can see over there. This case is different from the previous one because now I have considered parameter variation in the parameters, in the hardware parameters, and in the controller parameters as well. Here we have used reduced order sonotopes, and we were able to compute 10 million resets. This is an engineering problem that we have to solve in order to get this efficiency. And we could also analyze the parameter, the setting with varying all parameters for the first time. However, we were not able to handle the scenario varying all parameters and with jitter. Now, in Arch Computation 2020, which took place posterior to the submission of our article, we compared against other academic tools, and although the model is structurally simple, the problem still resulted computationally demanding for all the tools, and only two tools could run all the scenarios. Our tool is called Julia Reach. So here, Cora computes with sonotopes of order 20, and intersections with non-deterministic guards were calculated using constrained sonotopes. Highlevel computes in discrete time using support functions. SpaceX uses SCC algorithm as a model checker. It has to check after each jump whether the successor have already been visited, and this takes 90% of the time. For all the tools, the non-deterministic scenario poses complications. Let me now summarize our result. Our main contribution has been to unify existing conservative approximation ideas to give rise to a method exceeding the prior state of the art. And key idea has been to make use of structure and, for instance, pre-computing transition times and using specialized algorithms for parametric hybrid systems. We were able to demonstrate the approach in an electromechanical brake model representative of challenges in the automotive industry. Let me remark that the implementation is highly efficient and it's publicly available. We were able to handle the cases with parameter variation and jitter. We think that reduced runtimes will allow engineers to introduce more expressive messenger models with a relatively inexpensive computational cost. So there are some perspectives to our work. For example, we could improve the approximation quality in the presence of jitter by elaborating on the clustering strategy, and it will also be interesting to consider the interplay of our framework with a more complex nonlinear model. So thanks for your attention.